started, thank you for making it to the class. This is meant to be just an introduction. What we're doing this semester is a little different. We are going through recitation as opposed to doing full modules. So what we are going to do today is spend a little bit of time going over what two of the recitation will be about, because a recitation means that you've reviewed the material already, so that can't be today. We're just starting. And what I will suggest with respect to the two lectures, the module that I suggest are actually three of them, from the feedback we've got from the student, there is one specific topic. It's this one here on innovation via technology startup. There was just a lot of questions, a lot of views of this module online. So this is the one I'm going to suggest the most as something that you look at quickly at the beginning of the semester while you have time. And therefore, I want to cover that on the 17th, so that'd be innovation via a startup. And what has come up the most through that module that was live just last spring is how most of you guys students were interested in the case study, which is essentially the company that I founded with others about now 4 years ago. That's making a breakthrough innovation in how we do material testing. What I'll suggest then for October 1st is two main topics. One is, I say, essentially use of structural material. And that goes all the way from material selection, design, specifications, and essentially evaluating integrity risk, because everything can collapse. We see it all the time. You know, there's this bridge, there's this crane, there's this dam structure. Sometimes it's because of design, sometimes it's because of really how it was manufactured or constructed, and sometimes it's just not used the way it was intended to be. So those are the three main categories when we think of failure analysis. What that module does cover is World Trade Center and things like that. Personally, I have worked on the Macondo oil spill in the Gulf of Mexico, where there was intention to be able to shut that well. As we all know, it didn't work and essentially released for months. These are kind of one-of-a-kind situations, but essentially the process of failure analysis, which comes in that module at the end, it's a short session, is to learn from this. And this is where we have to be very humble as engineers, especially young engineers, to not think that a new idea is going to work the first time. There's just, when you try something completely new, there's a lot of aspects of design, manufacturing, and service that you can't easily anticipate. So we cover that in more details. And the other module is essentially more on how to make materials. So I'm just going to call it material processing. So from yesterday's lectures by Professor Eager, we very value student autonomy, your self-motivation to learn and gain experience the way you can through us by asking questions. That's really why we want to do these recitation. So I'm offering essentially 18 hours total here of material to view online, and you're welcome to email me questions anytime. Simon CB, I go by Simo. at MIT.edu. It's always useful. It's very hard for young engineer to gain experience rapidly. I mean, you hear in class, you learn about concept, you hear a lot of stories, but I think the starting point for experience is to multiple aspects. You put yourself in feet of others that have done this, that are willing to share, kind of like what happened. That's one aspect. But also you really engaging into what if you were in this situation, would you have different thoughts, like including like the topics I'm going to be covering in those modules. Well, it seems like this is also something important. And one aspect I remember vividly that came up last semester on technology innovation was how do you make your team? It forced me to develop some material on that, even though it is a topic that a lot of our sponsors, a lot of our advisors just want to avoid because it's so complex. But so it was a very, very valid question. It just generated some thinking, and I really value that as feedback from the class, interaction essentially. And what we're going to do today, again, we're going to finish the tape a little earlier and just engage and introduce each other here so we can move forward. So in that order, the innovation for tech startup, then structural materials, these are links. And I'm going to post that on Stellar so you can easily follow the link. And I got a big zip file that contains also all the PDFs of each lecture, so you have that as material available, because I know sometime on the screen it may or may not be the easiest. So this is all going to be on Stellar. The last one here about more material processing. It doesn't cover all material processing, this topic, this 6 hour here. I have another module that is available that speaks more about casting. But in reflecting on it, it is more of a scientific curiosity than a reality for most practical application, in the sense that very important for you to know that the metal from this chair was not cast, all right? It wasn't, because otherwise it'll be pretty brittle. So it's made out of straight tube that end up being cold form and all of this. And it's essentially, you cast that big billet and you reduce it, you make it a rod product. So it's very, very important for everybody to acknowledge that. And then there's welding. And welding tends to be in the areas that are not as strong because there's a stress concentration factor here. And it's just part of reality, because you don't want to pay more than, let's say, $25 for this. And therefore, it has to be very efficient into the making of this. And this is molded. So this is actually, one reason we use plastic is you can get them into final shapes more easily than you can with metals. So that really is what is being covered there, not only from a strength standpoint, but I've got half of this here on corrosion, on composite, polymer and corrosion. And if you look in the entire inventory for this class, there's not a whole lot. We talk really into the detail of plastic. So this is something that I know has been interesting for people working on composite, whether for research or other purposes. It's a brief overview, but I think it's something for you guys to consider getting engaged in that module and learning something. It's a very condensate summary of these different topics here and how to make materials. So between those three modules, there's essentially, just a little bit on my background, I was a PhD student here, graduated 2006. Then I worked for 5 years as a consulting engineer. And, it's a really large firm, and as a part of the engineering mechanics group, looking at different complex structures, working as consultant for others, doing failure analysis. Then I worked essentially as my own consulting firm along with others. We form a group of consultants, small group of consultants that still exist. And the focus there was essentially consulting services for design and manufacturing improvements. And then a big component ended up being failure analysis. So I've worked on just about anything that can break and be a problem that involves structural materials, from plastics to metals, mostly, not so many ceramics. I mean, I've done a few glass cases, but it's been mostly plastic and metals. So this is how I was, with that experience, able to think of some ideas on how to make structural material use more sustainable. You know, we have a lot of aging infrastructure. Essentially, I had a few ideas on how to do better testing for things that are already built. And that is what led to the startup. So without further ado, we'll step right into that. Technology startup. And what I decided to do, let me do it this way. I will give the module overview so you understand what the intent was. Technical innovation, to a large, there are other factors, but to a large extent, makes the United States stand out in the world. There is a lot of new technology, new ways of doing things that come out of our work as engineers and innovators. And a lot of it, especially in our community here around the campus, very diverse, and it's very entrepreneurial in how you can go from an idea to actually doing it. And I don't mean to say you have to take advantage of it, but I definitely invite you to consider this as really an opportunity. And one reason for the module, knowing that people have so many career paths, is as an engineer, in the next 10, 20 years, I would say about regardless of what you do, you'll end up being involved, working in collaboration with a technology startup. It just seems to be part of the process these days. So that's really why I decided to include it here in structural materials. And one specific challenge for this in the context of this class is a lot of how we use materials for airplanes, for highways, for automotive. It's been really developed over a very long period of time. And making a significant change, and we're thinking about composites to go in the Airbus, took more than 10 years. So it's very, very hard to think of sustaining something like that by a technology startup. And what ended up happening, from my standpoint, is not only you need a great idea, but you need the fire on somebody that needs that idea to be implemented really, really, really quickly. So essentially, by the time you have an idea, let's say the idea first is more of a technology as opposed to a customer need. You have to find that need. And I spent a lot of time in that class going over how you discover your customer and their willingness to help you help them. If you can't do that, and you have people that had invested in you, they get tired really quickly. So if you are, again, on a collaboration or on communication with a technology startup, it's again very good to understand that there's just a window of opportunity there, and a lot of these people do come from a very, very specific drive to take the idea to execution. I mean, because if they haven't convinced them of that, they haven't convinced anybody to invest in them. So you can take that for granted, that they do come from a background where they do have a lot of the requirements that it takes to be successful. But they need help from just about everybody. They really do. So the National Science Foundation has started this very large program for small business innovative research. And I want to highlight them because, to my knowledge, they are a very, very solid source of non-dilutive funding for when you have an idea and that you have also gone some preliminary validation on it. When I say preliminary validation, so here on campus, there's a smaller program that is intended to get you positioned to apply for this funding. There's a lot of resources available, and it doesn't apply to everybody. I mean, my background has been entrepreneurial from the beginning, from, I guess, growing up. And I go through the details in that class that entrepreneurship, to a large extent, is considering, analyzing, and adjusting risk. You make moves in thinking, well, if I take that risk, what's the payoff and what's the downside? And a lot of times, unfortunately, you have to be a little older in your career because the downside is it may not work and I may not make any money for 2-3 years of working on this. Okay, so that's something to think about. But on the plus side, if you join as a co-founder and you have an arrangement where you can sustain yourself with a base salary, it is a tremendous opportunity to learn really quickly something that's very, very hard, which is to go from, how about we do this, to actually doing it completely and fully. So my belief is we couldn't do too much of this. The entire process of arriving to an idea, validating it with some peers or potential partners to work with you, then interacting and discovering customers and really having an honest conversation with them. Is this something that they want or not want? And be very, very willing to accept, no, I'm not interested. And this is part of what's covered in the class, where the way you ask questions a lot of times drive the answer. It really is true. So you'll come and present an idea to a group of people where they understand you don't want them to say, we're never going to pay for this. So they'll say it's interesting. How do you come up with this idea? Does it really work? But it won't say the thing that from the approach you've taken, you're not opening that question. And I made a little bit that mistake, not terribly, but essentially, one specific way is saying I have this idea, I'm thinking I want to apply it for, an automotive wheel. Let's come up with any reason, anything. But we don't know if this is something that would really work or whether we should be focusing on something else. You just completely open the door to them advising you on what they think really is the application, because you're not telling them that you've already decided to develop it for that purpose. And it really is the right approach. So that's still, again, that critical review here of identifying your customer. And there's a process we call customer validation, which is very simple. They write a check. They haven't written a check, you haven't validated them. It's just, don't make it more complicated than that. Now, at certain points and through that process, you have to have a good pace. You have to be willing to make some mistakes and learn from it. It's a very, very dynamic process of going from an idea, working with suppliers, working with a team to get it from A to B to C to D, because in reality, there's a lot of fluctuation. So I talked a little bit about, with some examples from our startup, on how to take it a step at a time. I remember for us, we made a commitment 3 months with sending that final paper for presenting at a conference. We had nothing. We didn't have a piece of pipe. So now the clock was ticking to get to a point to be able to have a picture and have some data, say these is test data on a pipeline from our idea. And, if it validates, that's great, but, show a certain level of commitment to engage more in the discussion, like, now we have this, we need more pipes, so because there's always a process, in our case, with something so completely new to the industry, that you can't expect these people to be all of a sudden, yeah, I want to use this, like even if you had it fully ready. So there is a tremendous value in engaging very early when you almost have nothing. But a few nice pictures and a very clear thought on how you would do this. And just, be very honest. Can't take too much time. A lot of times you need some friends to get to the right people to have that conversation with. And a really good starting point is the people and the people that they know, and our alumni network. I mean, there's so many resources on how to go about to talk to people with a very specific purpose to discover. You're not selling yet. So there's a very big difference. The name that I was thinking about on campus that is awesome when I-Corps. So if you have an idea and you haven't taken it much further than thinking about it, the I-Corps is a program that you can actually get a little budget if you qualify to pay for time and certain things, like some marketing perhaps, to engage with customer. The program essentially requires you to have 30 conversation of 15 minutes with a lot of training on how to use that 15-minute effectively and on how to get that 15 minutes in the first place. Sometimes reaching out to people that can provide these introductions, and the important thing there from my standpoint, is whenever you reach out to people for any reason, you can assume they would like to help you. They would love to help you. So the best thing you can do is demonstrate, in an email that you send to somebody, an alumni, in 5-6 sentences, how in a short period of time they can help you, effectively. Because it's the worst annoying thing to sense that this is going to be a waste of time. This is not. They're not going to understand it. They don't want to hear what the story is. They're like sending an email. Oh, I've got this great idea. I know it's got a lot of application. All right, so we're going to spend 10 minutes, me now, lecturing on that, this may or may not work because they don't have customers yet, and there's a little bit of that. So it's something that was, very, very clearly mentioned that 3 paragraphs, 2 sentences each. First one, what you have, how you took it, and what you need help with. You can't, if you spend the time to do that, your ability to get help goes up tremendously. Now, you need to know that person, so what you say is what you think they can help you with, of course. But these big, long emails with a lot of attachments, just don't work, at least with me. In class, you can make mistakes, and I'll still take your emails and respond to you. Okay, so for the limited time that we want to spend on the record today, what I would do is tell you what I have been working on, and perhaps definitely a more succinct way than in that 6-hour module that we just provided the overview. And I'll add that I'm more or less committed to do a continuation of that module this coming spring, based on the feedback and based on some of the questions that came up, realizing that there's always more to cover, and it's a very long process. So my company, our team, developed new ways to test material for their strength and toughness that doesn't require cutting a piece of metal and sending it to the lab. The only current portable mechanical test is different versions of hardness testing, so indentation. We have a very, very different way of doing these tests. We actually have 2 technologies, and again, we've been working on this almost 4 years now. It started slow. We got our NSF funding, I believe, in first quarter of 2016. Phase 2 last year. Now we have a phase 2B. So the government has invested in us $1.5 million altogether in getting this idea to one market that has a big challenge: fireballs. This is an oil and gas pipeline that high pressure that ruptured in San Bruno, California in 2010. The National Transportation Safety Board, NTSB, did a failure analysis and concluded that the company who operated the pipeline didn't know the quality of the steel that was being used. The line had been tested with hydrostatic testing. They already had put water in it and did a pressure test to know if it will break tomorrow or today. It didn't. It broke later. A lot of people agree, well, yeah, this was a really, really bad material. Yeah, exactly, And the relevance of that for the pipeline industry is people just get very upset. Nobody likes the idea to have oil and gas on their property or behind their property. And the idea that it could just, you're sitting in your living room and all of a sudden it explodes, just, doesn't resonate with people. Nobody wants it. Nobody likes pipeline constructions. Yet, we need them. This was a lengthy discussion yesterday I had with people that are interested to invest with us, where if we don't have an oil and gas industry today, next year, in the next 10 years, it's not going to go well. We rely on it. People get upset if the price of gas goes up, $1 a gallon, but that's nothing as opposed to what the cost of energy would be if we shut down oil and gas. It just wouldn't work. Not just for really source of energy, but also feed into making fertilizer, making plastics, making all sorts of things that we just rely on, we just assume are going to be there for us. It's incredible. In New England, half of the electricity we use comes from natural gas. So you can drive an electric car, but at the end of the day, it's just, you're actually less efficient than if you were just running a car on natural gas. It's just people's perception of it that is unfortunately not well developed. So what that industry needs, the oil and gas needs pipeline. That's the network here, 300,000 miles. A lot of it was built post-World War II. There's a lot of economic expansion in the country, a lot of oil and gas production. So in the 60s, 70s, a lot of these pipes are now 50 years old. The cost of replacement would be, let's take one round number, $5 million a mile. You can't do it. You can't change all those old pipes. It's not going to happen. So what the industry needs is a better way to know which one specific section of pipe is the best to replace, like that 1% of your asset that you should be just replacing. Which one needs a lot of attention in terms of inspection and repair. Which one is just perfectly fine. And you shouldn't be digging it up just because it's got a little dent or a little nicks or something like that. It can't handle it. The problem with that industry is there's a lot of lack of records on the quality of the steel that was put in the first place. And as a result, they use a very similar assumption on the quality of the steel for a lot of these pipes. So that's the biggest challenge. And the way we solve this, just like I said on the first slide, is non-destructive testing, where we put the equipment on the surface of the pipe. And then we run a 10-minute test that essentially has the same level of variation that you get from sending a piece of metal to different labs that use different machines to run the destructive test. There's a lot of tools that are involved with this. Essentially, we use frictional sliding. So instead of indenting, we come on the surface and then we slide around. There's nothing really that's secret about it. We have a lot of patents on those two tools that we've developed. One is a sliding tool that makes a very shallow groove, and we apply a constant load and we slide just like a boat on a lake. It leaves a wake profile. We look at the width of that wake profile. It gives us a number of contact pressure during the sliding, and we have a lot of fine element analysis that we use to differentiate between initial yield strain and work hardening for all that, and then we go for blind test, and it works. The other tool is a wedge tool that has a little opening in it, and what happens is that opening gets the material to stretch and be subject to kind of a peel test, but it's in triaxial tension. So within our wedge tool, there is a small fracture surface being formed that is elevated with respect to the cut plane, and we're able to measure directly a crack tip opening displacement. So we make a very direct measurement of toughness. Those two technology are published in terms of how they work. It's really not the purpose of my summary, the idea here is if you have a pipeline and you want to know what's my risk of a rupture, you can look for cracks, dents, and corrosion loss, so that the wall thickness is reduced. You'll have a lot of that. And then the question is, what is the associated yield strength, work hardening, ultimate strength, and toughness for those assets? That's really where there's very little amount of information available. The reason they say there's a lot here is those big pipes, they're able to run an inspection tool on the inside, called a Smart Pig, collects a lot of information associated with that. It doesn't directly measure the material property. It can tell you, I got 3 miles of pipe that are just the same. So for those 3 miles, what needs to happen is to have our tool use at one location. So we started middle of 2014, just did a little competition here at Sloan. 15 is really when we started spending money and increasing a little bit our effort. We did get some government grant that really helped. We had to get really clear commitment that we were going to make sales if we did the very first phase of our projects, which we completed. And that just keeps leading to more things and more things. So this year, we're reaching for $1 million in commercial sales, specifically with these oil and gas company, and we charge a rate that's competitive. It's about 1/5 of what it will cost to cut out a piece and send it to the lab. But it's a good margin in terms of where we are today to help sustain us so we don't have a big burn rate as a company. And a couple things that I am very proud of is having taken the time to pick the right first place to go. And the reason for those pipelines is they happen to have gone through a lot of sales and acquisition, and therefore they don't have records of test certificate when the steel was manufactured. It's unique to them. For bridges, typically it's owned by the government. It's in an archive somewhere. You can pull it out and find out everything about it. So the sales and acquisition process was a big part of it. The other aspect is it was, the oil and gas boom, so the quality standard for that same steel were really not as stringent as today. And when those situations happen is not everybody makes bad steel, but some do. And if you don't know which one made which pipe, you have a big challenge. And they go through a lot of processes of trying to figure that out. And there's a lot of anecdote. Well, I got this pipe from this manufacturer. We had good experience with it. It's got some good toughness. And then somebody else, the same manufacturer, said, "Oh, I got really, really bad properties out of this vendor." Well, from year to year, from month to month, which machine were they running? What were the parameters? You don't know. You can only reconstruct after the facts. There's tremendous value in asset-specific data. That 10 miles looks like it's got these 5 different kinds of pipes. These are the properties of them. This is where they're located. Because when they run the inline tool, again, they're able to say, these joints are exactly like, oh, this one, slightly different. We should go and test this one just in case that's the rare occasion. And then by that, you're able to know, well, actually, we don't want to worry about it. It's better than the others. Or that's the one exception that could make the rule. So it's very, very difficult for that pipeline industry to completely avoid ruptures. But to some extent, the approach is to focus on detection of these rare situation through testing, as opposed to just assuming some bulk value for every case. A lot of those catastrophic ruptures essentially involve low material properties. Of course, they involve other things, but those other things, they're very, very common. You have dents from not only a mechanical damage, but also how they backfill the pipe into the ground. If that fill didn't had rocks in it, those rocks over time create dents. So you can have line segments that have thousands of dents, but you can't still economically pay for that replacement. So you have to know where in that line I have the steel that doesn't have the ultimate strength to resist a dent, for example, of a certain size. So it's where it's going, but it's process. You see the timeline here. It looks great. It's going up, but expenses are going up too. So it's a very, very challenging process. And we're at a point now where one of the ideas, we've proven the technology with blind test. We've created interest and awareness, and now it's to work with our main customer to make this useful to them. So when they're done at the end of the year, somebody say, why did you spend this money here? Well, we got that data. Now we know we can ask for a budget to replace this, and this is essentially paid by the ratepayers, the people that purchase the energy. But there's a reason. And it's not just based, well, I'd like to sleep at night, so I'd like to replace all the lines that have had some issues. That doesn't work. So the making, when you want to make a decision, you want to make an informed decision. And we are in the process of working with our customers to make their internal business case and how spending money today has a positive impact. Preferably this year, that's always preferable. And it will happen in the future because when you run these tools on the inside and you do a test on the outside, you can avoid having to keep digging that same line for smaller and smaller anomalies. Like you go for the biggest issues, you get some data on what it actually is in terms of size, in terms of material property, and you can eliminate additional effort of digging and repair if that data confirms that you don't have a bad pipe, essentially. So there's a very, very tangible goal there, but to be able to combine those two technology, what's done inside the outside, is going to take another 2 years. So right now, what we offer to the customer is you're going to have to decide if you're going to be making this line so you can inspect it on the inside. A lot of those lines you can't currently run a pig with this bends, these things that just prevent from using the tools that work on the inside. So should you spend that budget to modify your system, to run very expensive tools in it, to find anomalies, and then realize, oh, I got too many things to repair, and this is bad pipe property, so I don't want to do it. Instead of that, we'll provide some basic statistics. I've got 10 data points on this line. Looks like it's good metal, and it's also good welds, because we evaluate the welds with our tools, and that's really is part of what's unique, because the welding processes can vary a lot from mill to mill in time frame. So there's just an intrinsic value today, and one of my job is not talk to you too much about it, but keep talking to customers. So I end up being on the road every other week now to do this. And we're not done. We have a lot of other applications. We have components for defense, like helicopter, that have parts that have wear, for example, or corrosion, and be too expensive to redevelop the manufacturing process. So have a new forging made or a new casting made, the mold doesn't exist. They stopped making it. So being able to spray metal, for example, for structural repair of a component. We have transmission components right now for helicopter in our office that we're working on verifying how we can make our tools so it evaluates the quality of that structural repair so you can continue to fly the helicopter. And that wouldn't be any other way, because if the validation of the repair involved taking the thing apart, all of a sudden they keep losing more inventory in the process. So they don't have much to spare. So it's very, very tricky. very step-by-step process. At first they said, oh, we want this fully implemented next year. I said, well, we'll do what we can, but a lot of it depends on you. And the reality is a year turns into 2 years and then 3 years, but it's not 10 years. So these are tangible things because the helicopter is there, the transmission's apart. They can't get a part for it. They want to fly the helicopter. So it can't be a 10-year process. Very, very acute pain point there. So I hope this was a little bit of a good introduction on what this process has been for us. And when you go through the 6 hours, you'll see a lot more details on how the tool works and how we did some of the prototyping and things like that. How we figured out that we would focus on oil and gas, and how we've been thinking as of last spring, how we expand to the next market. And most of it is just absolutely true. So the only reason I'm saying I think I'll do a follow-up on this at some point in the future is not to replace any of the material, but just to take part of it as a little broader perspective, and perhaps use other examples that I'm very well aware of people would be willing for me to talk about as opposed to mine, because I know that it's something that you're interested in. And if you're interested, because you are learning from it. And the big thing to learn there is there has been plenty of times in that 3-4 year period that I really, really questioned, why I got into this. In my case, it was mostly year 2 to year 3, just when you're just close, but it's just very, very, very hard. And, today I'm glad I did. So we'll see how it goes. Thank you for your time.